Hello friends, welcome back to the series on physics of solids. For the last two sessions, we were discussing the lattice vibrations. There we discussed about the one dimensional monatomic lattice and the one dimensional diatomic lattices, and we derived the expressions for the omega, which is the frequency of the lattice waves, of the lattice vibration waves for both the situations, and correspondingly we plotted the graphs connecting the omega and k, which we call as the dispersion plots. And in the last session we discussed that in the case of a diatomic lattice, one dimensional diatomic lattice, it is having two branches for the dispersion plot. One we called as the optical branch and another we call as the acoustical mode or the acoustical branch. Now, in this session let us first of all try to see why there one branch is called optical and another branch is called the acoustical branch. So, as you can see the image there, the kind of vibrations which the kind of waves which both the optical and the acoustical branch possess are different. And also in the last session itself we told that in the case of acoustical branches, both the kind of atoms, the atoms M1 and the atoms M2 do vibrate in the same direction, whereas in the case of optical branches they vibrate in different directions. But still why the different names? We know that there are two kinds of waves, one we call as the longitudinal wave and another we call as the transverse waves. What is the difference between them? The longitudinal waves are waves in which the displacement of the medium is in the same direction or the opposite direction to the direction of the travelling of the wave, right. So, they are parallel. So, then in the longitudinal waves it happens in parallel. So, what is the example for a longitudinal wave? Sound wave. We have learned earlier that the best example for a longitudinal wave is the sound wave, whereas in a transverse wave the oscillations are occurring perpendicular to the direction of the energy transfer. So, if a transverse wave is moving in the positive x direction, its oscillations are up and down direction that lie in the y z plane. And what is the best example for a transverse wave? Light. So, therefore, as you can see there, the optical branches are having vibrations in different directions, which is perpendicular to the direction of k, whereas in an acoustical branches or in the sound mode the vibrations are occurring in the same direction or in the opposite direction, which you call as the parallel direction, as that of the direction in which the wave travels, which is parallel to the direction of the wave vector k, as shown in the image. So, that is the reason why we call the two different branches by the name acoustical and the optical branches. The vibrations of the acoustical branch can be generated by a sound wave incident on the crystal surface, whereas the optical branch can be generated by a suitable optical radiation, for example, an infrared radiation. Now, if we again look into the dispersion plot, in the region between the two branches you are seeing a gap, right. It is clear from the image which is shown there. So, we have a band of frequencies existing between the optic branch and the acoustical branch. So, what does the gap means by? A gap means that no amount of input radiation either the sound radiation or the light radiation cannot generate an excitation in that gap region. So, therefore, a diatomic linear lattice can be approximated to a band pass mechanical filter, right. So, in the case of a monatomic lattice also, we have assumed it to be we found that they do act as a high pass filter which acts between two different frequencies, and here in the diatomic linear lattice also we can assume to be them as acting as if band pass filters. Now, with this much concept on the two different cases of the one atom of the one dimensional situations or the one dimensional lattices, which is a monatomic lattice and a diatomic lattice. But in the reality, mostly you are having the three dimensional lattices. So, we will not be discussing too much detail into three dimensional lattices, because the computation of the frequency or the which will be really cumbersome, or it will be an involved process. So, we will not be embark into that area in this session, but we will slightly touch upon the three dimensional lattices. It is more a situation in the real lattices. But here also let us limit ourselves into a monatomic lattice, where atom in the primitive lattice is free to move in all the three directions. So, again if you remember, we started with the assumption of a solution for the displacement, right. So, here also one can start with a solution un equal to a into exponential I k r minus omega t. R is the x, y and z directions, right. So, you have the k x, k y and k z directions depending on the x, y and z direction. But in the three dimensional case, one gets led into three solutions with the ax, ay and az. There are longer steps for derivation, which we are not trying to do. A typical dispersion plot for a three dimensional lattice is as shown in the image. So, you have different branches within the acoustic and the optical branches, but here one should always remember that although there can be very clear divisions into acoustical and the optical branches, there can be cases in which there can be the longitudinal acoustic and transverse acoustic. Why that situation arises? So, if the wave vector is passing through a high symmetry axis, one can classify the derived branches as pure transverse and pure longitudinal, but that is not the case if we have low symmetry axes. So, that is why we have having the branches like LA, LO, TA and TO kind of branches. Now, the question is that can you predict how many branches are there depending on the number of atoms in a lattice? The answer is like this. So, if you have p atoms in the primitive cell, there will be 3p branches for the dispersion plot. For example, which we did for the two diatomic lattices, right. So, there we will expect that there will be 6 branches for the dispersion plot. So, of these 3p branches, how many acoustical and the optical branches? So, of the 3p branches, there will be 3 acoustical branches and there will be 3p minus 3 optical branches, right. And this equation is more valid for the 3 dimensional lattices. One should always take care to apply this kind of situations, in 3-dimensional lattices also in Ulli. The image shows the 2 typical dispersion plots obtained for germanium and potassium bromide. So, there you can see different branches which are plotted based on the calculations which are made. Now, so we discussed about the kind of lattice waves, right, and we talked about the different kind of branches which are possible. And now, the question is that can this wave, which is the elastic wave, be, can this elastic wave have a quantum properties? The answer is yes. So, what do you call it? The quantized elastic waves are what we call as the phonons. It is just similar to the other kind of quantizations like electromagnetic wave quanta. What do you call it as? We call it as photons. And then collective electron waves, the quantization is what we call as the plasmons. And then you have the magnetization waves, which we call as the magnons. And then there are other kinds of quantizations, which for example, polarons, excitons, etc. Now, coming especially to the quantization of the elastic waves or the phonons, the simple conclusion is that energy of a lattice vibration is quantized. We already talked about the normal modes, right. So, these normal modes are important because any arbitrary lattice vibration can be considered to be a superposition of these elementary vibrational modes. But a phonon is more of a quantum mechanical assumption or an observation or a conceptualization. A phonon is the quantum mechanical description of an elementary vibrational motion in which a lattice of atoms or molecules uniformly oscillates at a single frequency. So, that is what a phonon is being characterized, and this quantum of energy is what we call as the phonon. While normal modes are wave-like phenomena in classical mechanics, phonons have particle-like properties too, in a way related to the wave-particle duality of the quantum mechanics. And again, a phonon is often designated as a quasi-particle. It basically represents an excited state in the quantum mechanical quantization of the modes of vibration of elastic structures of interacting particles. Now, there is a good similarity with the harmonic oscillator. So, what is the energy there? We normally write it as E equal to n plus half h cut omega, right. So, that shows the discreteness of the quanta. That is how we pack the energies of a harmonic oscillator. Similar to that, here also we have packets of energy which we call as the phonons. Here also in the phonons we do have the 0 point energy, and if you remember that the 0 point energy is not necessarily equal to 0 electron volt. So, let us not have that confusion. And the phonons play a major role in many of the physical properties of condensed matter, like thermal conductivity, electrical conductivity, etc. Therefore, study of phonons is an important part of the solid state physics, or we call it as the condensed matter physics. So, who introduced this concept first? In 1932, a Soviet physicist, Igor Tamm, first introduced the concept of phonons. The name phonon basically comes from a Greek word phone, which translates to sound or voice, because long wavelength phonons give rise to sound. If you remember from our derivation itself, we have found out that process, right. And again it is having this similarity to the word photon. But although the phonons, the term might mean the might remind us of the sound wave, but the shorter wavelength or the higher frequency phonons are responsible for majority of the thermal process of the solid or the thermal capacity of the solids. Now the question is that you know that there is vibrations. You take any temperature, there is vibration, right, and you know the expression for the omega, and you have the theoretical models which allows you to plot the dispersion plot for any kind of crystal system, right. But now the question is that how to study the phonons, because you know that the phonons are packets of vibrational energies. Now, how to deal with the phonons, how to study the phonons. But the real problem is that if we need to really observe or to measure the phonons which are generated by the typical energies which is provided by a heat or by infrared radiation, it will be really hard for us to analyze. Therefore, scientists have devised a different technique which is purely based on the neutrons. Here what happens is that what we call as the inelastic scattering of neutrons, and this inelastic scattering of neutrons do generate certain lattice vibrations, and we study basically the energy, or we try to calculate the energy of the phonons based on the wave vector of the phonons. So, what happens is that here neutron is reduced to an energy of say 0.1 electron volt by passing through appropriate material. In the experiment, the neutrons are made to hit the crystal and the scattering occurs at a Bragg angle and also with lattice vibrations. So, at those which are scattered at the Bragg angle will lead into elastic scattering, and those which are which will generate lattice vibration, as you know, which might mean that will be leading to a case of inelastic scattering. So, in the case of diffraction, which we did in one of the sessions much earlier when we dealt about the X-ray diffraction or the neutron diffraction, there the elastic scattering was important. Here in this case, for the study of phonons, we will be taking into consideration the inelastic scattering. So, for elastic scattering, k dash is equal to k plus g, where k dash is the wave vector for the scattered neutron and k for the incident neutron. But for inelastic scattering, k dash is equal to k plus or minus q plus g, where q is the wave vector for phonon, right. So, what you found there, with this expression you can always calculate the wave vector for a phonon indirectly, because you have the techniques available already to find out the k and the g, and the rest part can be easily be calculated. So, in that expression for k dash for inelastic scattering, the plus sign means the creation of a phonon and negative sign means absorption of the phonon. So, the study of the phonons can necessarily help us in developing more better understanding of any crystal systems. So, we have dealt with different kind of lattice vibrations and the quantization of the lattice vibrations. Now, we are in a platform where we can deal more into the thermal properties of the solids, because we know that it is the thermal vibrations which we generated with the help of phonons, which we quantize them in the form of phonons. So, when we are talking about when we are studying the thermal property of any solid, one of the parameter which gets into our attention is the specific heat. So, what is specific heat? Specific heat is the amount of heat supplied to 1 mole of the solid to raise its temperature by 1 degree. So, this is the definition which you might have studied in your earlier classes. 1 mole of the substance, the solid is to be raised by 1 degree in temperature. In solids, there is practically no change in volume as the heat is applied. So, we always consider the Cv, which is the specific heat at constant volume, to be more important. So, the expression for specific heat is dq by dt, and dq is equal to, from your thermodynamics class, you know that dq is equal to is the sum of the internal energy and the work done. So, dE plus P dV, and for solids you have the dq by dt equal to dE by dt. So, what happens when you are applying temperature to a solid? Naturally, its internal energy will increase. In which form? Now, we know the answer for that. Now, that will increase the energy which you applied in the form of temperature will be spent in two forms. One is the increase in vibration of the atoms, and second in the increase of the kinetic energy of the electrons, right. At Cv, specifically at constant volume, when temperature is supplied, increase of the internal energy take place in two ways, which is the vibrations, which we call as the phononic vibrations, right. Energy which is absorbed by phonons increases, and we call that component of the specific heat as lattice specific heat. And the second part will be to give more excitation to the electrons, or the electrons will get excited to higher energies, which we call as the electronic specific heat. So, therefore, if we take a measurement of the specific heat of real solid, one can observe a dependence of Cv on temperature. For example, see the figure there, where we have the lead, silver and the aluminum and also the diamond, which is plotted, showing the relation between the Cv and the temperature. The graph implies that the amount of heat to increase the temperature by 1 degree is dependent on the sample temperature, right. Now, it was always an intriguing question for the scientific community trying to explain different kinds of thermal properties. Even after understanding much about the phononic vibrations and the phononic energies, is still a troublesome or a challenging question whenever we find out a new material to explain the dependence of the specific heat on temperature. So, over the years many models did came for explaining the connection between the specific heat and temperature. Mainly there are three models. One is the Dulong-Petit model, and the Dulong-Petit model, Einstein's theorem and the Debye's theorem, right. So, let us see what does the Dulong-Petit law means. So, in all these models there are certain central assumptions involved, which is very critical in deciding what this law will predict. In the Dulong-Petit law, the three major assumptions are involved. One, n atoms are there and they are equal to 3n harmonic oscillators, quite simple, right. And second assumption is that each oscillator in the crystal vibrates with a natural frequency, but they have different amplitudes of oscillation. And in the Dulong-Petit law, the main scheme or the central scheme was to find out the average energy of each oscillator and then multiply that by 3n to find the total energy, because that statement is very critical, because you will see that difference when we go into other models trying to explain the specific heat. An important application of the equipartition theorem is to the specific heat capacity of a crystalline solid. Each atom in such a solid can oscillate in 3 different directions. So, the solid can be viewed as a system of 3n independent simple harmonic oscillators, where n denotes the number of atoms in the lattice, and since each harmonic oscillator is having a total energy as an average energy of kBt, right. The average total energy of the solid will be 3n into kBt, and what is the heat capacity? It will be 3n kB, right. So, therefore, the resulting expression assuming equipartition theorem for the energy of the oscillation Cv is equal to 3 Nk, which will come, Nk means is equal to R, right, the universal gas constant. So, 3R is equal to 5.96 calorie per mole per gram Kelvin, or 24.94 joule per mole per Kelvin. But if we plot that, we will see that the expression or the 3 Nk will fit the real sample only at high temperature, because we are assuming that at high temperature the heat capacity or the specific heat not at all temperature dependent, right, because there is no temperature dependence in the expression which we have evaluated for the specific heat. So, as you can see in the image there, the dotted line shows the Dulong-Petit line, which is 3 Nk equal to 24.94, but the real sample behaves in the way which is shown by solid line. So, it is very clear. The Dulong-Petit law holds good only at high temperatures. So, we have a problem now. We have a model only which is valid only at high temperatures, and there were later lot of works being carried, lot of research work being carried out to improve upon the Dulong-Petit law. And the second more notable model was in the form of Einstein's theorem. He essentially used quantum mechanics to propose a new theorem for the dependence of Cv with the temperature. So, the Einstein's theorem and the model which followed, which is the Debye's theorem, will be discussed in the next session. Thanks for giving your attention to this session. See you next time. Thank you.